our NREN members and other ISP members can use this local Zoom facility. With the Zoom local traffic mark 1 Gbps. Recent network upgrade, we have replaced our core router, which was previous router was just 100 Mbps capacity. Now we have 10 gigabyte capacity router. Core switch also replaced and 100 Mbps capacity to 1 gigabyte capacity. Currently, we are working to several servers for the hosted in NOC, other purposes. We have a very other LMS and other. We are working for that. Network monitoring tools. We are using LibreNMS. This is a fully featured monitoring tools. This is open source, and we are regular monitoring and update for members, and we archive the graph from LibreNMS. Education, we are working, NREN will support necessary technical help to provide network connectivity in the government school for the network connectivity. NREN provide Zoom on-premises account to government school and community college. Connectivity is not good in rural area. Students are struggling to attend their online class. You can see a picture where a student from rural area is attending a class from a top of tree due to limited network coverage in the ground. A picture of Dhanakumar Magar, class 10 students, Nabarpur, Khotang district in east part of Nepal, making a pool on the top of tree is going viral on social media. NREN provided a Zoom account to his school. Thank you very much. If you have any query, please write email to info@nren.net.np or niradan@nren.net.np. Thank you very much.
Thank you very much, Mr. Niradan. Thanks a lot. And some really good work that you showed by Nepal NREN. So glad to hear and see that. So thanks a lot. Now, if it's the floor is actually open. If any other NREN, we still have a few minutes. Obviously, Pern is ready, but if any other NREN wants to go first, we can still have two presentations before the tea breaks, and then after the tea break we'll have the introductory session on software-defined networking from myself. Any NREN wants to present their work?
Dr. Arsalan, I'm from Learn Sri Lanka. I would like to do the presentation on behalf of Learn. Can I?
Yes. Thank you. Sure. Yes. So Learn presentation. Please go ahead.
Yeah. I hope you can see my screen.
Yes, we can see your screen. Thank you.
Okay. And I have also started my video. So my name is Tabotaran, and I'm a member of the board of directors of Learn, Lanka Education and Research Network. And I'm also a senior lecturer in computer science at the University of Jaffna, Sri Lanka. These slides are prepared by our director of Learn, Professor Roshan Ragal. In addition to me, there are a couple of other members of the Learn community in Sri Lanka are also participating in this work training program. So Learn, a small introduction about the organization and the structure of Learn. LEARN is established as a company in Sri Lanka, Lanka Education and Research Network, and in 2009. And since then it is there. And we have a membership from 18 full member institutions and 15 associate member institutions and 19 affiliate member institutions. And each different category of members have different kinds of access and rights to the resources of LEARN. And it is the LEARN operations of the LEARN is governed by the Articles of Association of LEARN 2009. And there is a LEARN board of directors coming from each full membership institutions. We have universities, 18 universities across Sri Lanka, and they are the state universities, and they are the full member institutions in LEARN. We also have 15 associate member institutions, different institutions and research institutions and higher educational institutions. They also come under as associate members. We have 19 affiliated members, which are semi-government institutions or government departments, and some are total private institutions. They also become as affiliate members of LEARN. LEARN is managed by a set of board of directors and coming from each full member institution. Chairman of the board is appointed by the University Grants Commission. A board also appoints an exco who help with certain operational decisions, etc. We also have a board meeting regularly every other month, and the executive committee meets whenever needed. And this is the structure of the LEARN arrangement. And we have consultant and the CEO, we call him as the director. And under him, we have chief technical officer, assistant operations manager, manager human resources and administration. Under each category of these managers, there are different experts, network experts, financial experts, and operational management experts. They are working day and night to provide the LEARN services to the LEARN community. And if you consider the LEARN network status, LEARN network and the network services are monitored and approved by the Telecommunications Regulatory Commission of Sri Lanka. And it is not only a internet service provider, it is more than that. And LEARN provides connections physically and virtually with other regional and global research and education networks. And it also enables accesses to various projects, resources, and training programs targeting towards the research and educational networks. LEARN also provides technical assistance centers, virtual conferences, educational IDs, LEARN Identity Access Federation, and also EduRoam, which is a global access to network services. And LEARN also conducts time to time its own training and experience sharing workshops. And this is the kind of the network architecture that LEARN is having. We have global connectivity, and also with the support of local internet service providers. Some are private, some are state-funded network service providers. We are providing network connectivity to our member institutions. This is the bandwidth requirements in Sri Lanka. You can see the beautiful picture of the country, and at different ends in the country, we are providing connectivity for various institutions and the higher educational institutions. And we also have, as a national NREN, we also have connectivity to all other countries and their NRENs with various capacities and direct links. Therefore, we can access services. We also have attained connectivity from LEARN. And LEARN's role in online education with the COVID-19, universities in Sri Lanka closed on March 19th, 2020. And within 4 days, with discussion conducted along with the government support and also with other internet service providers, Learn IPs were whitelisted, and internet services to access educational activities from higher educational institutions was given to students and academia for free. And since then, we have been enjoying the free internet facility to conduct lectures, online classes, and to access those facilities for free of charge. So students or any academic staff or anybody is not burdened with any financial constraints to continue their studies. Learn also provide data visualization by collecting Zoom meeting data there and providing them to the institutions. Therefore, they can visualize and see how the resources are actually used. And this is the usage of monthly video conferencing from Learn Zoom activities. So number of participants are again going up and up again. This graph was as of September 2021, and now the government is planning to open the universities for lectures and exams. So these may go down because when they come to face-to-face, there may be less number of Zoom training programs or Zoom classes conducted, get reduced. And this is also video conferencing meeting minutes. And Learn has recently introduced a number of services, eduid.lk, and it gives an recognition, and also as an academic or a student, they can get usernames and passwords for free, and also get access to other services for free. And you can also access EduRoom, that is another facility from various popular places where you can see the hotspots, train stations, bus stations, hospitals, universities. Students and academics who have this EduRoom active access can access the internet services for free. So Learn also has local and international engagements. Learn conducts from time to time various training programs to local and international participants. These were conducted in a face-to-face manner when everything was under control and we were not under pandemic. And Learn also conducts various other training programs. Learn in 2019 celebrated its 30 years of existence in Sri Lanka. And even in collaboration with Lanka Network Operators Group, it has conducted various training programs where participants from other partnering countries have also participated. This is also one picture from one of our training programs where members have participated. And I think that's pretty much about Learn and its operations and an introduction to about Learn to our members. Thank you very much. I'll stop here. Dr.
Thank you very much.
Yes.
Yeah, thank you very much, Dr. Thabutaran, if I'm pronouncing your name correct.
Yes, okay. Perfect. You can call me Tabo.
Okay, thank you very much, Tabo, and wonderful presentation and a very good insight about Learn and its activities, and very nice graphics in the presentation. So thank you.
Thank you.
So I guess we can have a last one from our own NREN from Pearl. So they are here physically. We have a time for one more presentation. So please, Mr. Umar Tariq, Deputy Director, Transmission and Networks. So if you can just briefly, we have 7 to 8 minutes before the tea break to talk us about Pearl. Thank you.
Assalamu alaikum and hi everyone. I hope you can hear me. Thank you, Dr. Arsalan. I am Umar Tariq. I'm working in Higher Education Commission of Pakistan, which is actually the custodian of Pakistan education and research work in Pakistan as well. Starting from a brief history of PERN, it was an idea under an IT action plan in 2002. It was initiated with the name of Education Intranet. So initiator in Pakistan was the Ministry of IT, and we have some sponsored from Pakistan Telecommunication. Executor was at that time National Telecom Corporation, and PTCL was the implementer. Now, currently, the custodian, this network was handed over to Pakistan Education Research Network was handed over to Higher Education Commission, which is the custodian of this network right now. Well, we started from a very basic network, which was sort of a legacy network, a TDM-based network. You can see a very low bandwidth capacity was available, and we had connectivity between 3 major cities of Pakistan. At that time, there were 58 universities which were connected on PERN network. The uplink bandwidth, the total uplink was 155 Mbps. So there were some challenges which were being faced by the PERN-1 network. It was using basic telecommunication infrastructure. It was not aligned with the modern NRENs. Next generation services was a challenge, and there was limited bandwidth available on this network. Next. In 2006, due to these challenges, it was decided to upgrade PERN network to align it with the modern NRENs and the requirements being faced. So a proposal was submitted, and under that proposal, 10G network was established in 7 major cities of Pakistan. It connected the 7 major cities of Pakistan. This was a DWDM based network with the 10G metro rings established in 3 major cities, 1G last mile connectivity, and 15 POP sites were established as the universities were partners. So the 12 were established at the universities. This is you can say a high level diagram of PERN-2 long haul network. We have 3 rings covering all over the Pakistan, and we have about 6,000 plus kilometer of this optical fiber network. This is a DWDM based network, and the core or the backbone was the 10G, which was initially designed at the time around 2007-8. Next. Okay, this is the review of the 3 rings which we have. These rings have 10G backbone. We have 3 rings, and we have about 18 spur sites which are directly connected on this ring. It covers or spans from 51 cities all across the Pakistan, 22 ADM sites, and 25 we have OLA sites, 1G last mile capable network, and we have some of the STH based links as well. Now, this was the platform established. With this, we then started connecting our higher education institutes in Pakistan. Next, please. So when PERN-2 was planned and executed, there were about 80 HEIs connected. Bandwidth requirement was very low. HEIs were using very basic services. But with time, the number of HEIs increased, their demand increased. The services which they were using, they also got very critical. They were hosting data centers. So the availability of services was a very demanding thing at that time. So there were few upgradations that were planned. Next, please. So in 2016, it was planned to upgrade PERN-2 network. The expansion of this network, sustainability of existing infrastructure, HEIs, service enhancement. So with the help of government, a PC1 was approved with the title of Strengthening of Core Network and Expansion of PERN. So next, please. So this is what was done. basically we upgraded as we were using BWS 1600 system at that time. So we upgraded to OSN 9800 OTN based network. And these are the few upgradation which are being highlighted. We upgraded OLA to ADMs. We added new sites. We upgraded our core network sites, and we used the OSN 9800 equipment, which is provided by Huawei. Just a representation of what upgradation has been done. Next. Few links were upgraded to 1G to 10G. Our core network was upgraded from 10G to 40G. New links were added. Next. So this is a low-level diagram of what actually a nodes look like in our network. This is just an example of our node installed in Islamabad. This is an OSN 9800 system. We have FIU boards, then we have amplifiers, we have demux, then multimlux, variators, again amplifier, and we have these FIU board. In between, we are using the tributary and line cards, and we have this 10G supported line guards and tributary cards, and we are using multiple of 10G lambdas to get the capacity equivalent to 40G. So this is an overview of PERN evolution. We started from a core bandwidth of 2 Mbps, and very few sites were connected. And now ultimately, currently we are standing at PERN 3, which is a 40G core bandwidth network. And last mile we can provide is 10 Gbps. So these are the numbers of higher education institutes which we have connected. From 2002, we started from the 16 institutes, and at 2020, we were standing at 345 institutes that were connected through this network. This is the footprint which we have grown through the years. 2008, we were covering about 7 cities of Pakistan. In 2020, we have footprint at 74 cities nationwide. So we have few things which are coming up in our network. One of them is, the span of the rings is very high. We have a ring 1, which is about 2,000 kilometers, and a ring 3, which is about 3,000 kilometers. So we have decided to bifurcate them for higher availability of the services. Moreover, we are also growing and expanding in one of our west core side, covering the new cities, and it will also add the number of rings in our network. Next. So the platform is available. Now, what are the services which are running on this platform? One is we are providing the internet and intranet connectivity, the NREN connectivity to all the institutes of Pakistan and educational and research institutes. Other than that, we have digital library, smart university, video conference. These are some of the services which are running on this network, and the institutes are using these services. Next, please. This is one of the example of smart university service. Currently, we are here in NUST, and in this campus, we are using these services. All the students and faculty members of this service, this institutes are already using these services. And wherever you go, you have a full coverage blanket, and all the institutes which have subscribed for the services in Pakistan have complete coverage of Wi-Fi, and the PERN network is extended throughout the buildings. Another service which is being offered is a safe campus service. Basically, this is under the service, security is being ensured and monitored throughout the campus of that institute. We have a number of universities which we have connected under this safe campus project. Also, we are providing national video conference services Our partner institutes are already using these services, as we have plenty of bandwidth available, a state-of-the-art core backbone network available. So a very good platform is available for such a service. So the institutes are already subscribing to this service and they are using this videocon service. It has also medical applications, which you have seen in this. This is all from our side. Thank you very much.
Right. Thank you very much, Mr. Umar, for the presentation. I think that we can have a break of 15 minutes now. Any of the other NRENs would just like to speak up, and give a message, or yes, please, Mr.
Yes,
Pong.
I'm KW Pong. Yes, from Harnett. I prepared a couple of slides to introduce Harnett to the member. Can I share my screen?
Right, sure. What we can do is, in fact, let's go ahead with your presentation. Yeah, because you are ready. So please go ahead and share your slides and tell us about Harnett.
Yes.
Yeah, thank you.
Okay. Okay, hello everyone. I'm KW Pong from the Harnett. I'm the technical support of Harnett. I will using a couple of slides to introduce a short introduction of Harnett and the recent development. Okay. Harnett, the full name is Hong Kong Academic and Research Network, which links up. Okay. Oh, which links up the 8 universities in Hong Kong and connect to the global internet and other research and academic network, such as SDON and Asia Connect. Harnett is operated and managed by the JUCC, a joint university computer center, which is a consortium of 8 government-funded universities. Harnett is, of course, an advanced network infrastructure to facilitate the academic and educational research and collaborations for the country. In recently, we deployed one NUC, which is mainly for connecting the external or global NRENs, and it is formerly called Hong Kong Open Exchange, but now we are renamed it to Harnett R&E node. The purpose of this node is to increase collaboration and achieve resources sharing within the global community. And now this is the Harnett infrastructure. You can see this design is the Harnett R&E node, which is located in Mega I in one of Hong Kong data center. And we connected with SDON and CSDNet and CloudNet and NICT and SingleRAN. And another, we also have commercial connections with the Google, AWS, and Apple. And recently, we upgraded the Select 2 connection from 10 gig to 100 gigabyte. And here is another part of Harnett infrastructure. This is the Harnett core network that connect 8 universities in Hong Kong and providing internet connection. And also it has connection to the Hong Kong Internet Exchange and some cache server over the Harnett infrastructure. And this slide is what I was showed before. And the most recent event is because is was decommissioned in January 2021. So JUCC joined the partnership with NRENs and NICT on the 10 years IRU of 100 gigalinks, which is shown in the red circle on the AppleNet diagram. This is the AppleNet diagram. And you are welcome to connect to HARNET RNE node. That is research into Hong Kong can work effectively with counterpart through the connected NRENs. We support two types of connections. Of course, layer 3 mode and layer 2 mode. We can run a Q-in-Q VLAN to help you to ping your network to another NREN. And we also have a BGP peering over the layer 3, so we can share the routes between NRENs. Oh, this is our overall traffic of the HARNET RNE node. The maximum is around 10 gigabytes. This is 2021 June. If you want more information, you can visit the URL over here. And this is the HARNET RNE node for official website. Or you can, over there, you can send an email or fill up the form. You are welcome to join us. This is my short introduction to the HARNET. If you have any question, you can send the emails to hartep@jucc.edu.hk, or you can visit www.jucc.edu.hk. Thank you.
Thank you very much, Mr. Pong.
Yes.
Thank you very much for the presentation and for talking about HARNET.
Yes.
I think as per our schedule, we should have a 15 minutes break now.
Yes.
And if there are other NRENs who wish to participate, what we can do is that we can squeeze this session right here. So you can just write me an email and I will plan these two sessions accordingly. And we can have so for example the remaining NRENs, if they wish, if they wish to talk about their activities, you're definitely more than welcome. So please just write me and I'll squeeze a little bit the plan accordingly. Okay, so now I think we can have a 15-minute break. The physical participants will have a tea break, and for the online participants, I would say you can go and have some break and a tea or cup of coffee, and or maybe if you want to keep, you can. I think the chat is open, but if you want to have a break, please. Although we'll continue the session again after 15 minutes. So we are a bit late on time, but let's make it 11:45 Pakistan Standard Time. So we'll start with the introduction on software-defined not optical, software-defined networking. So we'll have that session. Okay. See you in 15. Thank you. Dr. Imran, you're here?
Yes. Hi. Good morning. Good afternoon. Whatever, wherever you are, everyone. Can you hear me?
Yes, we can hear you.
So, should I share my screen or you will start? I think.
Okay, I can share the screen. Let me just download our presentation. Right. So everyone, as per plan, this is the last short talk, and in this talk, me and Dr. Imran will discuss about specifically about this very project, the software-defined optical networking lab project, the rationale behind it, the objectives and scope, and this training is one of the deliverable of this project. Okay, so right, so right, so Dr. Imran, you will you may start at the early part, and then and then I'll take it from you when the project details comes in. Okay.
Okay. Okay. Yeah. Okay. Allow me to share my screen then, please.
Okay. So.
Okay. I think I can. Okay.
You can. Yeah. I have made you the co-host. So please go ahead. I'm not sharing the screen. Am I?
No. Okay.
Okay.
So I hope now everyone can see.
Yes, we can see. Please go ahead. So we are a bit late on our schedule. So
I'll be I'll try to be brief and quick. Okay.
Sure.
Good morning, everyone.
Sorry to say, sorry, before you start, Dr. Mohammed Imran is the senior researcher in School of Superiore Sant'Anna, Pisa, Italy, and SSSA Pisa, Italy is also our basically in everything we are collaborating in this training event, in the establishment of lab, and in everything. And Dr. Imran is the coordinating PI of this project, and I'm the PI from Pakistan side. So thank you very much, Dr. Imran, for joining, and please, over to you. Please go ahead.
Okay. Grazie mille for the introduction. Thank you. Okay. So in this talk, we will discuss mainly the project rationale, its objectives, what we plan to do, what we were able to achieve. And it is, as Dr. Aslan, maybe in the morning, I couldn't join the session. He had, I hope he has discussed that about the donor agencies, Asia Connect and the TNCC. The project is supported by them. So I'll quickly move towards the, sorry, just a minute. Okay, towards the SDON. So as Dr. Aslan just discussed, the SDN paradigm, it promotes the separation between the data plane and the control plane for the automation of the of the network. So, but simply put, we can say when we talk about the SDON, it is an optical network which is integrated with the SDN. And the main motivations behind the interest is to have the programmability, automation, cost reduction, using the SDN-enabled orchestration and the control. If we exploit the SDN concepts, both optical hardware and the software can be disaggregated, and then we can connect it through the suitable APIs like southbound interface, northbound interface. And then optical disaggregation is just like, I will explain a little bit. It's like, we use to build our PCs, you take things from different places and then you put it together. So it's not so simplistic as building the PC, but it's the main, we can build an analogy. And optical disaggregation, it offers a flexible and the modular network architecture. And open ecosystem, from operational point of view, we say it will increase the supply options for us. But here we will be mainly focused on the software defined optical layers and mainly optical layer planning and hardware, physical layer issues. So mainly I have in the first slide covered this part that we segregate the software and the hardware, and they do communicate through the APIs. So the software controllers and the management control plane that gets the network information from the devices. In case of optical, it will be line systems and the terminals, and then they send the network actions back. And those actions can be performed in the connected devices. There are different options, as there were also questions in the previous session. You can have the open source software, or you can have a proprietary solution as well for the controller or even orchestrator. Or open APIs, they actually define how applications they communicate with each other, with the hardware, even on the upper level through the northbound interfaces. And when we say open hardware, that means it supports allows to control a third party, or we can say third party controller to control that devices, send commands to that. But of course, it should be a multi-source agreement agreed between the parties. So standardization is in place, is in progress, I would say. It's not in place. So we will discuss about that. So this is a little bit of it. And when it comes to the optical network, we can say that the two main elements for the optical link are the transponders and the line systems. Transponder is basically responsible to translate the client data into the optical layer characteristics, do optical to electrical, electrical to optical conversions, do some FEC, some other features. The line system is mainly we can say it's our transmission layer, optical layer, where we send the data from one place to another, and all WDM technologies and other stuff comes in that domain. So here, if we look at, sorry, just a moment, it's something else. Okay. Currently, the networks we have are aggregated, fully aggregated, where we have an end-to-end system which is supplied by a single vendor. It is managed by a single managed system. And mostly the devices, all the devices, the key elements of optical link, that is the transponders, terminal multiplexers, inline amplifiers, reconfigurable optical add-drop multiplexers, or all of those are mainly from one vendor. I know there is a support of alien wavelength as well, but it's has some limited features, and we don't have usually all of the control about that. So the idea in the open and the disaggregated is that to avoid the vendor lock-in, we should go with the open support and the open network, open standardization, like using the concepts, bringing the concepts of the SDN into optical layer. So in this way, since it's very, I would say, the responsibility of the transmission layer of the optical networks is too high, because all of the traffic is being carried about them, and especially on the line system side, the optical layer requires, there are so many physical parameters that must be optimized and agreed upon between the vendors, and building a consensus is not so easy. So far there have been two different approaches: partially disaggregated and the fully disaggregated. And we can say this is the near term, and this one can be the long-term solution. So in this way, here we in the partially disaggregated, we basically segregate the transmission layer, the transponders on side A and B, and the line system separately. So that means the transponder can come from one vendor, and the line system can be from another vendor, and that those can be managed through an SDN controller that could be provided either by transponder manufacturer or line system manufacturer or any third party manufacturer. In the fully disaggregated case, it is a kind of a wish list or ideal scenario. People are working on that, especially the Open ROADM consortium. And in this way, the idea is that all the devices have standardized APIs like transport, and they can be from any vendor. Even people thinking that A and B side of the transponders could also be from different vendors, but that would require a lot of agreements for the interoperability. So in summary, we can say that when we move from aggregated systems to disaggregated, open and disaggregated system, we have two options: partially disaggregated and the fully disaggregated. In our project, we tried to build our lab based on the partially disaggregated frame, but of course, in the future, it could be moved towards also fully disaggregated. It has the potential. There are different initiatives going on, mainly the telecom infra project, which was the main reason behind it, and it has a very broad scope. And I would say optical layer is just one part of it. And there is also Open ROADM, Open Config, ODTN. You guys can check, after the talk and see what their scopes are. But there can be different views which level of disaggregation one should have, partial or full. But the desired level of the SDN and the desired level of SDN automation we want to have. But we can see with the certainty that almost the current operating models, engineering skills, both in academia and also especially in the industry, they will not be sufficient, and we will need new skills and expertise that must be harbored for planning, engineering, deploying teams, and of course, like in academia, also the research should be done. So basically, a collaboration between the academia and the NRENs in this regard would be really helpful. And now Dr. Slan, you want to start from here, and then I'll take later on.
Sure. This has always been our joint presentation. Maybe some of the audience has seen in one of the APAN. You want me to go from here, and then just let me know from where you want to take control once again. Okay.
All right.
Right. Okay. So yes, thank you, Dr. Imran, and Dr. Imran briefed about software-defined optical networks, and which we also call the open optical networks as well. So you will see speakers tomorrow and in the remaining days using the term open optical networks more as compared to software-defined optical networks. So anyway, the rationale and objectives obviously were built on top of what Dr. Imran has already discussed, that the goal is of the project is to establish a software-defined optical network training laboratory as a future platform in Islamabad, NUST Islamabad, Pakistan, in order to bridge the skill gap in optical network domain, and between the R&D research and education communities through capacity building and research collaboration among TN and NRENs. And this training, we see this as an opportunity of building the capacity of TN and NRENs, also as an opportunity to extend a message for future research collaboration in this domain. So the scope of the project involved training network and operator specific research for capacity building, planning and procurement teams of TN and NRENs. Yes, okay. So our project, which is obviously near to it, was these are the particulars of the project. Me and Dr. Imran were the PIs, the budget and the project period. The project structure is divided into 5 work packages. So WP1 is the overall project management, which is being done by both Santana Pisa and NUST. And then we had the WP2 work package 2, train the trainer, work package 3, establishment of SDON Lab, work package 4, SDON and operator specific challenges. And this particular training falling under the WP5, work package 5, workshops and trainings. In this, we have given 2 workshops on in APAN 51 and 52, sorry, 50 and 51, and also this SDON training. Please go. Yes. The participants of the project, and with this slide, we again would like to thank all of them. So Santana Pisa and NUST were the project partners, and PERN and TN are the facilitators. So TN facilitated and helped us a lot in the global procurement of the equipment, which is now placed in the SDON Lab at NUST 6. And then Learn, BDREN and MyREN are the project partners, and they have extended support in nominating for this training as well, and also for the student research, which will be carried on further after the training. It got a bit late because of the COVID situation, but it will proceed further even after the completion of the project, with 1 Learn researcher and 1 MyREN researcher involved. So far, the capacity building through research and training, what are the outcomes? So if we talk about student research, 3 NUST students have been involved, and we have started hosting one of the Learn and MyREN student research. And the student research output so far is 1 research publication published in Wiley MOTL, another one in optical engineering, not mentioned here, and 2 conference papers. Once again, one is mentioned over here, another one is not mentioned here. ONDM and the Optical Tropical Summit by Optical Society of America. That one is not mentioned over here. And then the training event plan in Pakistan, which is continued right now. Today is the first day. So in particular, the work package 4 talks about the SDON and operator specific challenges. So it is vital to understand and quantify the impact of introducing these new technologies in terms of operator perspective. And so just few slides ago, Dr. Imran talked about the optical network disaggregations. And so definitely it avoids vendor lock-in, but then when you disaggregate things, then someone has to take the role of integrator as well. Dr. Imran, if you want to add in this slide as well, in particular, please go ahead, because work package 4 you have done a lot of work.
Sure. Okay, but the question is, we can disaggregate, but who can do the job that the integrators, basically the mainly telecom service providers, telecom equipment providers used to do, and that's a big question, even for the large operators in the first world. Only the I would say the OTTs, they have this capability to build and maintain their own teams and even manage that. But slowly, things are improving, and this is an important, I would say, aspect which must be explored before taking this decision by the operators, that which level of openness, which level of disaggregation I would like to have. If I want to move there, how I'm gonna migrate, what would be the impact on my operational mechanisms, my procurement strategies, my planning strategies. So these are the important questions before the operators, before taking any decision. Previously also, we used to have new technologies, but probably they are more or less standardized. They follow the OIF, ITUT standards, and we knew how to manage those things. But when we are going to have our own element management systems or NMSs or orchestrators, it's going to be a bit difficult. So we have worked on that. I think in the tomorrow afternoon we will have a very detailed talk about that, and I will share the studies we did, and also some recommendations for the NRENs, which were the deliverables for this project. And I must say, we are open to even post-project collaborations for the research activities with the academias, both from PERN and also Asia Connect partners, and also with the operation teams of NRENs to advance the operator specific research as well. So, okay, so can I move on?
Yeah, sure. I mean,
Yeah. Okay.
one of
All
us.
right. Sure. Okay.
Yeah.
This is the structure of the lab which we envisioned, and hope more or less it is done. There are still some parts which are, we are working on it, and I hope we will do it. So the idea is that I already said that we are going to build a complete WDM link, a single link, not a network. We can say it's just a point-to-point link for now. And it is based on the partial disaggregation model, where the transponders and the ROADMs, they are from two different vendors. And basically, I would say they are not from the conventional vendors. They are pure open hardwares. They are bare metals in which we have to have open source, the drivers, APIs, controllers, everything would be open source. So that we have the leverage to work on it, to do some research work, to learn more and share with each other. There are proprietary solutions as well, but so the idea is we have a pair of transponders and pair of ROADMs or open line systems, which is basically an integrated ROADM that includes all the building blocks of a ROADM. I will explain later on these. And they are all managed, then we have the two servers, two machines which will be running ONOS as an open source controller for this, and that would be our SDN controller. And we will also have, we have all this setup already established, and it is connected to the NUST network and the PAN, and soon we will extend it connectivity to the Asia Connect partners. And it will be equipped with also to emulate the links. We will also have, it is on the way, I would say, the fibers, and we will also have the fiber links, and the spectrum analyzer will be there for fully, and essential test instruments to measure. So this is just to let you know what we will have, so that in the future we can have some collaborations. I'll skip this. You all are probably familiar. Okay, I'll quickly go through this because the people who are from the transmission background, they know that optical networks designers and the operation guys, they are always going through the transformation, because we are the carriers of all types of traffic, and we have to accommodate the bandwidth requests of all kind of services which come to one's network. So from the design perspective, if we segregate the two things, operator's perspective and the design vendor or designer's perspective, the challenges are like this. The designer has to provide more and more capacity, longer distances. There should be resilience in the network. Resources should be efficiently utilized, both even the energy efficient. And it should be even adaptable, because we have to accommodate different type of traffic, also different type of customers, and also from the operational point of view. From the operator perspective, on the other hand, the important things are first of all, low total cost of ownership, maintain the quality of service, efficient OEM, and if we are a commercial entity, and NRENs mainly are not per se commercial entities, but the conventional operators, they want to return on investment, and of course smooth migration. So in this way, also so these challenges we will also have when we move to, I would say these challenges must be carefully taken care of when we go towards the open networking, especially the how we're going to do smooth migration, how we are going to ensure the low total cost of ownership, and how we're going to maintain the quality of service. So the main drivers of why now open and disaggregated has come and not before. This was a kind of a wish list in the operators to not to be dependent on one operator in general. But as the SDN progressed, but also in parallel there is I would say the drivers and the enablers are also the flexibility and the programmability in the optical networks. The compactness and the modularity that has come because of the photonic and electronic integration. Signal processing has advanced because of the coherent detection and coherent receivers. Of course, there is also a market competition and to ensure also the interoperability. Okay. Now, a little bit background. I'm giving this background just because before I explain the specifications or the features of our transponder and the vendors, so the people who do not have background, they can have a little bit of idea about that. The traffic is unpredictable. There is a network dynamics or also in play. So there is a need for a network that can adjust the resources based on the traffic solution. So in the past, I would say 3, 4, 5 years back it started, and now even the vendors have the products. Elastic optical networks or the flexible optical networks, they emerged, and this flexibility was envisioned in all the domains, starting from the spectrum itself on the fiber to the transponders, cross connects, control plane, planning and management in all the layers. When we talk about the grid, I will be a bit quick because we are getting late. Otherwise, we could spend time on that. Traditionally, the spectrum of the fiber, for the optical communications, we work in the C-band, the conventional C-band, and ITU-T for the long reach. For the short reach, we are in the O-band, which is used for the client interfaces. But for the WTM networks, mainly, the C-band is divided into chunks of slices, which are 50 and 100 gigahertz standards. And it has been in use since last, I would say, 20, 30 years. And there were 10G previously, 10G, now even 100Gs and higher data rates are in place. And these grid was going fine. But when but there was some problem and efficient when we have the flex, because of the flex grid, we do have some advantages. I give you an example how we can get some advantages. Now the ITU-T grid has been updated, and there is flex grid extensions or flex grid. The provisions have been added into the standard. So here is an example that if we have 100 gigabits traffic signal and that is passing through the 50 gigahertz, this fixed grid should be fine for us, But what about the 400 gigabit signal that requires more spectral occupancy than the 50 gigahertz? And here if we will pass through that, the filters within the system, they will cut part of the signal, and we will not be able to have the error-free transmission. So this flex grid is the solution that gives us the possibility to move the spectrum slices and allocate according to our need. And that leads to actually the spectral efficiency, because the limited available spectrum we have on the fiber in the C-band, especially, that we can use more efficiently. And this flex grid concept, we can say it is realized through the tunability in the laser, or tunability of the wavelength or frequencies, and also the wavelength selective switches in the ROADMs. Here is an example when we have a multi-rate signals. If we use fixed grid, here you can see that is how they will be arranged if we have the 50 gigahertz, and you can see that the spectrum is being wasted. But if we have the flex grid, the same traffic that can be accommodated in this much spectrum. So we do save our we become more spectrum efficient, I would say. When it comes to the flexibility in terms of the transponder, I call this flexibility wheel. These are the options we have in the bandwidth variable transponders. If we wanna, depending on what we want, uh, whether we want the high spectral efficiency, capacity, distance, we have multiple options. Of course, we can go for the higher order modulation format if we have the coherent detection. QPSK 16 gram and higher, we can increase the baud rate. That would complicate the electronic side. So there are, depending on the application and the network domain we can make those choices. We can do dual polarization or single polarization transmission. If we have OFDM-like transmission, we can have the electrical carriers multiplicity. If we want to extend the reach, we can go with the LDPC, FAC, or different type of codes. Or if we can also create the super channels, where we can have optical subcarrier multiplicity, and those super channels basically are managed at a single carrier, single managed entity. This is I took from a paper, very interesting depiction of how a bandwidth variable transponder can be. Here you have the client interfaces, control interface, and the line interfaces. But you have the possibility to select the modulation scheme, the effect, code rates you want to have, symbol rate you want to achieve, the wavelengths you can tune, number of carriers, and the client per port, what you want. So this is an interesting depiction that actually makes the concept more clear about the transponder. Another enabler is basically the integration, electronic and the photonic. Electronic integration was there, but still now we have, I think, reached to 14 nanometer, even less, 8 nanometer also, I think. And also I would say the photonic integration as well. Like if we want to create the super channels of like, these are how many, 6, then we needed all of these equipment, 6 with the carrier, the modulators, lasers, also lasers for the local oscillator. So there is a big footprint, but the same thing, because of the photonic integration, that could be in these chips, that can be accommodated in those chips. So that lowers the footprint, and then brings the modularity and the compactness that is very important for the space efficiency, for the energy efficiency, for the competitiveness in the prices, and those things help the operator. Okay, this is an example, just an example. This is an old example where here we see how we moved from modular cards to the CFP modules for the 100G. This is the impact of the material when we, in the photonic integration, if you use different type of materials like lithium niobate, have a little bit of they need longer waveguides and the modulator size is bigger, indium phosphide. And if we go to silicon photonics, how we get the advantage in terms of compactness, but they do all of those also have their pros and cons. This is not the topic of our talk. And here we see an example of a single chip silicon photonic transceiver, just in a one pluggable module. This is the latest thing I just want to show. I picked yesterday. It is the 400G QSFP, dual drive, I think, yeah. Or I don't know exactly the abbreviation, but this is OpenZR. These are called, these are interoperable as well, and they support the open optical networking as well. These are very recent. And essential features of the open transponder, some essential features: it should be modular for the low startup cost, to reduce the sparing cost, so that we can go as we pay as we grow. And it should be flexible in the line and client interfaces. It should support multiple types of interfaces, pluggable optics, as we discussed. It should support flexible line rate and the reach. Wavelength should be tunable. It must support, of course, the NetConf based open APIs, which can be, or even the proprietary APIs, and standardized based on the standardized information models. And it should support third-party SDN controllers. Now about the line system. The optical line system is mainly responsible for the optical functions like mux, demux, switching, amplification. I will show in detail all those functions, and they are basically done in a optical node. But it should support a variable channel widths, channels, variable channel spacing, signal rates, fine granularity of the optical power monitoring. The amplifiers in it should have the gain and tilt control. They should operate, support automatic gain control, automatic power control, even current control if possible. Modes of operation. There should be flattening algorithms for the BSPS. And MUX and DMUX should be also support flex grid. There should be optical channel monitor, a module in that, and optical supervisory channel as usual, which is the conventional. It must also be supported. So now coming to the what we bought based on that. Our transponder is from EdgeCore, which is Cassini. This is, I would say, the latest product, the only advanced product than that in the open optical networks is the Phoenix, which is just accessible to one or two operators who are part of the design and is not probably yet floated. And our transponder, basically it has the 8 line slots, and you know, it can support 100G or 200G line rates, and it can support different modulation schemes as we discussed, QPSK 8 QAM and 16 QAM. It has pluggable optical modules, and the line side of what we bought is basically CFP2 DCO that can be used as 100G and 200G. And there can also be ACO versions. The difference between the ACO and DCO is that where the DSP resides. And then we have the client side. We have 16 ports in total, and that can support USFP 2800G or even 40G and the 20G. What we did in our lab is that we bought these direct attached cables, which basically split the 100G interface into 24 into 25G, and that we will connect to our network interface card in our servers. And then those will be connected to this transponder Cassini, and they will connect through this line side to the ROADM itself. And we bought the Lumentum ROADM. It's a company which is used to supply, I would say, modules to the system integrators like Huawei, Ciena, Ericsson, and they have this. This is an SDN-enabled open ROADM, which is very compact, but it does have 20-port twin wavelength selective switches, booster amplifier with all the features which I discussed earlier. It has the channel monitor. It can also do total power monitoring and even the per channel monitoring. Probably in the lab visit or sometime Dr. Salman and the team can show the interface. It also has its user interface. And it does support the netconf and the YAN all support. And we are now the team is actually working on building the we have made this lab operation kind of operational, but we are now building because it is open source. So we have to handle APIs for each and everything, for the line card, for the CFP2, for the switch servers, switch softwares, and the people are working on it. This is the internal structure of the, I would say, ROADM. As I said, when we coming, the input signals, they are, okay. The input signals from the client, from the transponders, they come into MUX. They are multiplexed through this multiplexer, and this is a wavelength selector switch. There is a booster amplifier. These are the monitoring points, which are internally connected to optical channel monitor. There is a provision of optical supervisory channel. There is a possibility of attenuating the power if you want. There is a VOA in it. While the receive side, we have the preamp and the supervisory channel. Of course, is we can here demultiplex that or segregate that from the main signal, and then we have the DMUX. It is basically the WDM principle, and then it can be connected back to the transponder side. The possible configurations in the lab we can have is basically, since we have the two, we can connect two transponders together through the optical fiber link, and still we can have a controller on top of that. And this will be, we can say, a short distance link or a data center link. It can emulate that. We can have OLS to OLS connectivity as a point-to-point line system. We can have a partially disaggregated system in which we have the basically this is the thing which we have built and still working on its controller side now, and where we can have the OLS from different vendor, which is Lumentum in our case, and we can have the Cassini's, the transponders from one vendor. In future, in the Open ROADM, they also believe, actually, I think in 400 GZR, they are trying to even demonstrate that. I'm not sure, but I think so. I read somewhere that the transponder on the A side and the B side could also come from different vendors, but that's a big ask, I would say. It's a bit complicated. And then we can also have connect the two Lumentums together to build a 2-degree ROADM. This is the wish list for us. The future, we want to have the ROADMs from another vendor as well. Even we can try to build a ROADM using our own devices, buying the amplifiers and the multiplexers and building them together. There probably, if it is confirmed, there will be a talk tomorrow from the CESNET if they, how they build it. So this is it would be a kind of a network which we will have in future, hopefully. And I thank you all. If there are questions, please.
Right. Thank you, Dr. Imran.
I hope.
Yes,
yeah,
please.
You're not sleeping. Okay, thank you.
Yeah, they have to show us they are not sleeping. Any questions, please, from the audience here?
I know it's
And,
lunchtime. But...
yeah, we have just passed a bit of our schedule, but that's okay. So the participants who have joined online, yes, we have a raise of hand. Please go ahead.
We have a question after your lunchtime. I will not disturb you right now. I will ask you after your lunchtime. Sorry for that.
Okay.
No.
If you have a question, no problem.
Yeah, please go ahead.
Happy to entertain.
Okay. The question is that at least the optical. I would like to know if the SDON they have the what we call the ability to detect, let's say, the fiber is cut within the distance, let's say 10 kilometers or 5 kilometers. With the SDON, can it detect or not?
Sorry, with the SDN, can it?
With the software-defined optical network, can it detect, let's say, how long or we can say that the distance that the fiber is cut?
Okay, so Dr. Imran, he's asking that if there is a cut in the fiber, can SDN help us in locating that fault, that cut?
Well, yes. Okay. First of all, even in the current systems, there are when I talked about the resiliencies, there are protection schemes, standardized schemes, even coming from STH. Even they are supported in the OTN, where the fiber cut is detected, which is basically because in the amplifiers you have the alarms are triggered, and there is a automatic laser shutdown features and things like or detection of if the signal is lost, and that triggers the how to say, it can be on the multiplex section or the path protection, but the signal is the cut is detected, and the distance doesn't matter in that. The cut is detected and it is triggered. The resiliency is triggered. How software defined? Okay, the alternate solutions, people also have built-in modules for like OTDR modules built within the systems and that do the active monitoring of the network, and that can also be sent to the signal, because they are transmitted, this information we receive through optical supervisory channels. How SDN can enhance that is because of the how to say, enhanced monitoring features in the hardware, but using all that information and the network statistics, like people are working these days using the AI to predict the cuts, or to be more proactive and do better monitoring by utilizing all the monitoring information we used to have in our EMSs. Because previously we used to have a lot of information, but that was just coming as, and we were just observing it. It was not being processed for the network health, I would say, to improve the network health. But this will be probably some of the vendors are also offering, but it has to come with the combination of the data link layer and the network layer both. This enhanced services. And I can say, being a physical layer guy, that the data link provides all the things which are needed for this. I hope I answered the question.
Okay. Thank you for that understanding.
Okay, so there is another question in the chat by Lawrence. Thank you for the question, Bhutha. And Lawrence is asking that what are the challenges we are facing in SDON compared, and which sides need more development, northbound side or southbound side? You would like to take that question?
Yeah, some part of it probably you can tell, but anyhow, it's like, when it goes to the control plane, then, from the optical side, the main challenge is to build a consensus among the vendors, how much information they want to share about their device. And even for, for example, people have, for the optical layer, people have different algorithms and the proprietary solutions for managing the line side impairments, the PMDs, dispersion compensations, or they have their proprietary designs for the transmitters and the receivers, which are optimized in this way. They actually, how to say, compete how far one can go. So these are actually the main challenges, that how to ensure interoperability and how to build a consensus among the vendors, that how much information they want to bring into MSA, the multi-source agreement. This is one of the main challenges. But overall, the challenges were SDN compared to SDN, which side needs more development? Northbound side. Okay. Right now, I would say the southbound interface is more or less agreed upon. There is probably not transport API is one of the solutions that provides the connectivity for the transport network in total, covering north and southbound interface. But still, there is strong work is needed on the northbound interface. How to connect private networks using SDN router? Dr. Islam, please. You can.
Okay. How to connect private networks using SDN router? I think thank you for the question, Mr. Nirajan. I probably covered it in one of the answer in the question for the previous talk. I mean, you can simply use an IPsec tunnel. No, I did not cover that question. No, sorry. Yes. And at the end of the tunnel, so basically the gateway router of the private network and the SDN router where it is hosted, they has to be on the same IP network, and then you can, I believe, you can manage the private network with the help of SDN router, which is part of the other router, which is your local or campus or whatever WAN site. But with the help of IPsec tunnel, I think that you can create you have to designate one gateway router of the private network, and then you can have a P2P network of those two. And then with the help of IPsec tunnel, I think that the controller can act for both local side and also for the private side as well. Okay. Um,
I had a sorry, yeah,
yes.
just one. I had also had one question sent to me by an old friend who is in the audience. He's asking about some operators network here, whether its NOC is not disaggregated approach. I would say, you know, those kind the NOCs we have in conventionally in operators that support that are able to manage the networks from different vendors. So it's like, you know, connecting the islands. They have different element management systems, and then they can take information from those element management system and club them in one OSS or NMS, you know. So it's kind of an SDN approach. You can say it's like an orchestrator, but does not give you the leverage or the control that is available with the SDN, because that is just the you know, taking the information from different. For example, if you have your WDM networks or optical networks in two different regions, their EMSs are actually brought into one NMS, and that can be a third party, but that is just the information that EMS wants to give you, and that doesn't allow you to actually play with the devices itself, you know. So that's much more than that. That's the higher level of we can say aggregation of multiple vendors solutions, but that is much different than the software defined optical. I hope I answered the question.
Yeah, he's smiling, so I think you have answered the question.
Okay. Okay.
Right. So, okay. Thank you, everyone. If there is any further question, we can take it at the start of the next session, because I'm receiving calls that the food is waiting for the physical participants. So thank you, Dr. Imran.
Thank you.
And I think we since we are actually 30 minutes behind schedule, so what we can do is that we'll start at 2:15 and we'll have a 45 minutes lunch break. Okay, so we'll start at 2:15 instead of 2 at Pakistan Standard Time. Okay, instead of 2, we'll start at 2:15. And see you guys at 2:15. Okay, thank you very much.
The virtual guys can enjoy the lunch at their places.
Yeah,
at their own
lunch.
cost.
I think most of them, lunchtime has been passed. They are ahead of us, so they can enjoy.
Sorry
an
about
evening.
that. We wanted to host you guys, but we couldn't, you know. So
yeah.
Okay. Thank you.
See you in 45. Thank you. Thanks a lot.
The conduction. Now you can see that there are some more electrons in the conduction band when we provide the to these electrons that we have in the valence band. So if the electrons from this conduction band, if they now move back into a hole, they will give all of this, and that energy given in the form of light would be in the form of a photon of light, right? So if we look at if you compare the structure with respect to the energy level, so that can be seen in this diagram. You can see we have it's simply a PN junction. A semiconductor laser diode is simply a PN junction. So we have a P-type material and we have an N-type material, and in between them we have the depletion region. So if there is no voltage applied to this N and P type material, then the electrons and holes, they are normally they are in their positions and they do not move across. So this depletion region, it's a sort of barrier for the motion of electrons from one point to another. If we apply a voltage to the terminals, meaning that a negative voltage here and a positive voltage here. So for example, you have these laser sources in a pointer that we use in our lectures. So that pointer has a battery inside, a DC voltage source. When you press the button, you are connecting the N type of that laser to the negative terminal of the battery and P type to the positive terminal. And this makes the electron to move from N to P region. So when they move from N to P region, they need to be given some energy. They are getting energy from that electrical source. When they reach the P region, they find out many holes are available for them. So they recombine with holes in the P-type material. And as a result, the energy that they had obtained from the voltage source, they give up that energy in the form of a photon. So that's how it's as simple as you can see here, that's how a semiconductor laser diode works. So we have some spontaneous emission as well in this case. Like, so spontaneous emission means that there are some undesirable, so you gave energy to the electron and it combined the whole by, it was, for example, if you give energy to the electron, it combines with a hole before a photon stimulates it, right? So that would be a waste in a sort of a waste of the energy that we had given to this electron, and that appears as a noise in the signal. So it's called the spontaneous emission. So one is stimulated emission, that is the desirable effect. It has a higher percentage, and one is the spontaneous emission, which is an undesired effect. So a further requirement of the junction diode is necessary to establish lasing. So if you give energy to the electron, it recombines with the hole and gives energy in the form of light, then that's not just the only requirement. You need to make an oscillating cavity. So there should be some optical feedback principle. And for that, we need to polish the surface of the laser such that the light, when it hits this cleaved surface, it is reflected back. So in effect, it forms a cavity. So this is a typical structure of a gallium arsenide homojunction laser diode. The P-type material here that's connected to the positive terminal. We have the N-type material connected to the negative terminal. This is the PN junction. In this, these are the cleaved surfaces. They are cleaved such that they reflect most of the light that falls on them, right? So, of course, their reflectivity is not 100%. Otherwise, this light will remain confined within this region. So they have reflectivity, for example, like 99%. So 1% of the light comes out that we use as the laser source. Why do we want multiple? Why do we want the rest of the light to be reflected inside? Is because we want to cause more and more of the stimulated emission. And so this process keeps on, and this cavity works. There's a standing wave inside it, as we mentioned earlier, and this cavity works as an optical oscillator. So the light output versus the current is it's a typical plot of a diode, right? So we have, after some threshold, the stimulated emission starts, and we get a significant amount out of our laser source. So some of the semiconductor materials that are used for this purpose and the wavelengths that they emit are discussed here. So this can be found in any literature quite easily. So the next step is optical modulation. So we have the source now. So the next thing is, how do we modulate this light source with respect to our electrical signal? So there are two types of modulation. One is the direct modulation, and the other one is external modulation. So direct modulation, as the name suggests, as I said, we apply a voltage to the laser source in order for it to emit light. If we superimpose our signal, this baseband signal is the data signal that we want to transmit from one point to another. If we add this to the DC bias that we are applying to the laser diode, then the output light will vary according to this signal, right? So we superimpose the electrical signal with the DC source, which is used to bias the laser diode. And after that, the output of the laser will be varying according to the baseband input or the electrical input that we have applied. So this is called direct modulation. We can pass this signal through fiber and we can photo detect it, amplify it, and low pass filter. So this is the receiver part of it. So if we look at it from the transfer function of the diode, so we have current on this side and laser output here. So we bias, we apply a DC voltage such that the laser diode is emitting this much of light, right? After that, for example, our baseband or the data signal is a sinusoidal signal. We add that to this DC bias. And so it should be biased such that the positive and negative excursions of our electrical signal, they are adjusted in this linear region. So when they are adjusted in this linear region with the variations of the electrical signal, the output of the laser will vary accordingly. Output power of the laser will vary accordingly. So you can see, since we are connecting the data directly with the bias of the laser, so this is called the direct modulation. In this case, we have considered an analog signal. We can do this for a digital signal as well, where we have two levels, either one is positive and one is zero. So in that case, the bias should be somewhere here, so that for zero voltages or negative values, the output is almost zero. And for positive values of the electrical signal, the output is some significant amount of light. So this is called the direct digital modulation. Now, direct modulation has some issues, that is the data rates that we apply to direct modulation, the electrical signal that we apply here, it cannot generally exceed 10 gigabits per second, because the laser response is not fast enough compared to, like, if we increase the data here more than to like the value of 10 gigabits per second, around 10 gigabits. So then the laser response is not so fast. And so there is a limitation to the direct modulation. So in order to cope with that limitation, we use external modulation. EOM means electro-optical modulator, means the RF input is given, or the electrical signal is given as a separate input terminal. The laser diode is given at the input, the optical input of this device. And so at this point, the output light is modulated with respect to the electrical signal, and then we transmit it through the fiber and photodetector. So this gives us much higher bandwidth. We can apply signals up to 60 gigahertz. So mainly we use a Mach-Zehnder modulator for this purpose. Mach-Zehnder modulator, this is the typical structure of a Mach-Zehnder modulator. The electrical signal is applied to these electrodes that you see in the gray portion. The way it works is the input light is divided between two paths. Depending upon the voltage, one of the path is delayed, or the phase shift in one of the path is more compared to the other. And when they are combined here, depending upon the voltage, it's either a constructive or destructive interference, and the output of light is modulated according to this input electrical signal that we apply here. So this is a typical Mach-Zehnder modulator transfer function. On the y-axis, we have the normalized power, and on this axis, we have the voltage. So you can see we obtain a linear, almost a linear region over here. So this is the point where we use, we apply our data signal, the electrical data, to obtain an optical signal that is modulated with respect to this data. According to this data, it is modulated. So then the next thing is the optical fiber. After the transmitter, we have the fiber part. How the fiber works is basically on the principle of total internal reflection. If you see, you may have noticed that if you put a stick into water, the part of the stick that is inside the water, it seems to be deviated slightly from the input part that is outside the water. So this is the basic principle that is used in the fibers as well. So this is the incident light. There is some deviation from this angle. So the exit ray has a higher angle with respect to the normal. So if we move this incident light towards this side, this follows this, the exit ray, the angle phi 2 gets larger. And there's a certain value of the incident angle. It's called the critical angle, where this becomes exactly 90 degrees. The phi 2 becomes exactly 90 degrees. If we increase the theta 1 beyond this, if we increase phi 1 beyond this phi c, the critical angle, then we get complete reflection instead of refraction. So there is no refraction, all of it is reflected back. And so based on this, you can see that we always need to input the light at a certain angle in the fiber to cause the total internal reflection to continue its propagation through the signal. For this, N1 and N2, these are the refractive indexes. They should be different for the two materials, right? So generally, the N1 should be, it's the other way around, should be higher than the refractive index of the inner, where we have the input side should be higher than the output on the opposite side. So this is the way, as I said, to make the light confined inside the fiber. So we have a core. This part is core. It has a high refractive index. We have cladding. This part is the cladding. So we are looking at the side view of a circular shaped fiber. So if these angles are maintained according to the principle of total internal reflection, then the light keeps on propagating through the fiber. There's a certain acceptance angle that we need to maintain. If our input is within this acceptance angle, then the light will couple into the fiber and will keep on propagating. If we move ahead of this, outside this cone of acceptance angle, for example, ray B, then the light will not propagate. When it hits this point, after hitting this point, that is the boundary of the core and cladding, it will not be reflected back. It will move out into the cladding, and eventually it would be lost in the cladding. So there's an acceptance angle within which we need to transmit our light signal. So based on this acceptance angle, there's another term that is commercially being used for fibers, that is the numerical aperture. It has this acceptance angle inside it. N0 is the refractive index of the air, that is the outside, whatever is outside the fiber. This is the acceptance angle, and mathematically we can prove that it's the difference of the squares of N1 and N2. So you can see by choosing suitable values of N1 and N2, we can control the acceptance angle and the numerical aperture of the fiber. So one type of fiber is the step index fiber, where the difference in refractive index from core to cladding is in a step shape. So we have this as a core. You can see on this axis, we have the radial distance from the center of the fiber, and on this axis, we have the variations of refractive index. Inside this core, the refractive index has a high value, and suddenly in a step, the refractive index is reduced when we move out into the cladding. And this makes sure that the light that is input into the fiber remains inside. The core diameter generally for a multi-mode fiber is in the range of 50 micrometer, or it can be like 50 to 60 micrometer. And in this way, it will not allow only single, it will actually allow multiple modes of the light to propagate through the core of the fiber. So this was a multi-mode case when the light has multiple modes, because the spacing is large, so those modes can propagate through the fiber. If we want only the single mode transmission, which is the fundamental mode, then we need to reduce this core diameter. So previously it was around 50 micrometer. For single mode transmission, it should be between 2 to 10 micrometer. Right, the fiber is still a step index fiber. So we have this step, and the refractive index varies from this value to a lower value in a step. And in this case, only the fundamental mode of the laser, input laser, propagates through the fiber, and the rest of the modes are not allowed to propagate because the dimensions of the core are very narrow. So another type of fiber is graded index fiber. In this case, instead of having a step variation like this, we have a gradual variation, right? As you can see. So for example, this is one variation, one type of variation between the core and the cladding of the fiber. So it has an advantage compared to the step index fiber. As you can see, the different modes in this step index fiber, they are propagating through different distances. And so the same signal will reach, for example, if here you have the receiver, the same signal will reach this receiver at different times. So that is an issue with the step index fiber. So by using a graded index fiber, where for example, it has a profile like this, a profile of the refractive index, the different modes of the laser, they propagate almost at the same speed. So for example, at this point, all the modes are combined. Even if we, let's say, place our receiver at this distance, you can see the light, the part of the light which started at this point, most of it is received at the same point in time, right? So this is the advantage of using a graded index fiber, that the difference in speed between different modes is small. So the modes travel at almost the same speed. Now, the dimensions of graded index and these fibers are, so if we have a step index multimode fiber, the core has a diameter in this range, 60 to 50 micrometer. The cladding has a diameter of 125 micrometer. This is for multi-mode propagation. So multi-mode fibers are generally used for example, data centers, where the different racks and different data centers are connected. The distances involved are low. So you can use, in that case, you can use multi-mode fibers. The next fiber is the single mode fiber, SMF. The core diameter, as we saw earlier, is in the range of 8 to 10 micrometer, and its cladding has the same diameter as 125 micrometer. So this fiber is generally, it allows only the single mode to propagate through it, and so the distance that it propagates is much larger compared to the multi-mode fiber. So the submarine cables that we see, that we know that they have a distance of around thousands of kilometers, so they generally use single mode fibers, right? So fiber has an issue, as every channel has impairment. So fiber also has impairment, and this plot shows the attenuation profile of a fiber that we've seen earlier as well. You can see that around this region, this is a logarithmic scale. So somewhere here, the lowest value of attenuation exists, which is the 0.2 dB per kilometer. And so that is why this is the main reason why the communication takes place in the 1550 nanometer wavelengths, because the attenuation of the fiber is smallest in this region. So the next impairment that fiber induces over the signal is dispersion. So if we have a digital signal, it is being transmitted in the form of pulses. So 1011, for example, this optical pulse, after propagating through the fiber, after propagating some distance, each pulse spreads out, right? So if it spreads out, there is a probability that if this effect is not fixed, then there's a probability that the pulses, the adjacent pulses, they overlap. If we allow them to further propagate, after that, the adjacent pulses overlap so much that it becomes difficult to differentiate that what data pattern was actually being transmitted. So this is called dispersion, and this plot shows the value of dispersion for different wavelengths. So for example, for a 1550 nanometer region, somewhere here, the dispersion is around 16 to 17 on this axis, 16 to 17 picosecond per kilometer per nanometer. So dispersion is related to the delay, right, of the different frequencies of light. So as I said, if we tune a laser to 1550 nanometer, then it will not necessarily, it's not that it will only transmit 1550 nanometer. It will have some bandwidth, like 1550.5 or 1549.5. So all these wavelengths would be included in this laser source. So the dispersion is because each wavelength has a slightly different speed of propagation through the fiber. So this is why the pulse disperses, it broadens in the time domain. And so because it's related to the delay, the propagation speed, that's why we see a picosecond, the value of time in the unit for this dispersion. So this for standard single mode fiber that is being commercially used, the dispersion, as I said, is around 16 to 17 ps per nanometer per kilometer. So there's a method to correct this. We can, if we have attenuation, we can fix that by using amplifiers, optical amplifier. If we have dispersion, that can be tackled by using dispersion compensation techniques. So what the simplest technique is to use a fiber that has an opposite dispersion profile. So if you look at this, the with an increase in wavelength, the dispersion is increasing almost linearly, this dispersion. So if we design a fiber whose dispersion decreases with the wavelength, so we can place them back to back with each other, and in this way we can compensate for the broadening of the pulse. So if we look at it on a plot, then this is how it looks like. We have the signal at the transmitter side. It passes through a standard single mode fiber. This is how it expands. After dispersion compensation fiber, we can bring it back to almost its original shape, right? So this is why DCFs are used. The other way to tackle this is to use dispersion flattened fiber. So dispersion flattened fiber will, for example, in this region, its dispersion will be almost flat, right? So the different frequencies in the signal, they propagate with almost the same speed. And so the signal at the output of this fiber will not be very different from the input. So that completes the channel part of my talk. The next is about receivers and the amplifiers, but I think I have covered I've taken the 1 hour that I had for the talk, and there will be another talk like for a half an hour talk on Thursday as well. So I'll complete this presentation in that talk. And so this is the end of my presentation, and now I'll take any questions. If the audience has any questions, I would be happy to answer. आपको नजर आता है? Can you see it? Yes, please. So yeah, so if I'm pronouncing it correctly, it's Wutha Ket. He or she has a question. I'm sorry, I can't tell the gender from the name. So yes, please ask the question. Ask to unmute.
Hello?
Yes, Wutha,
Can I
please ask the question.
Okay. I saw some optical fiber that is the standard. It's called OM3 or OM4. Is it limited the bandwidth by that standard or not?
I'm not sure if there's any technical issue because I can't hear you.
Can you hear me? Hello? Hello? Hello?
We can hear you.
Okay, so
Can you hear me?
if anybody else has a question, feel free to ask. You think there's some issue? Yes, because that's the chat box should be where I'm not very good at this. So yeah, chat. So you can also type in your question in the chat box. So it seems there are no questions. Right. So that's the end of the talk. Listening. And sometime I'll invite Dr. Aslan to discuss the next talk. Yeah. So their standard of cable OM3 is the bandwidth limited by the standard or by the SFP. So the standard is basically based upon the design of the cable. So OM3 is for a multi-mode cable, multi-mode fiber. So the thing with that multi-mode fiber is easy to design because, as you can see, the core radius is in the 50 to 60 micrometer region. So that's more easier to design, and it's basically cheaper to manufacture. But the issue is that it cannot transmit data to a longer distance. So that's why it has been given some standard that for these particular wavelengths, sorry, for this particular bandwidth and this distance, so it's the bandwidth distance product. This is the standard for the fiber. So can you please write down what you mean by SFP? Because I'm assuming it's
the ASP here I refer to, let's say, if we use the ASP plus or ASP, is it the bandwidth between the two devices limited by the ASP?
In general, I would repeat that the standard is given based on the structure of the fiber, and it's the structure of the fiber that determines the bandwidth and distance it can propagate the signal.
Okay, understanding. Thank you so much.
So now, like for example, the commonly used fiber for data centers is multi-mode fiber because they are being used in a large amount. So we need to have a relatively inexpensive fiber. So they're easy to manufacture because of the larger mode radius, but they have a lower bandwidth. Now, since the bandwidth requirement is increasing even in the short distances that we have in the data center, so these multi-mode fibers are being replaced with single mode fibers, even though they are expensive, but that's the one of the options to increase the bandwidth in data centers. For the longer distances, the only option we have is the multi-mode fiber. So I hope I've answered your question. If
Okay, thank you
there's
so
any
much.
further question, you're free to ask. Right, so it seems further questions. So I'll ask Dr. Arsalan to continue the session. Thank you.
Thank you very much, Dr. Salman, for the talk. In fact, we will continue, but after a short break. So we are going to have a tea break here now, and that will be of 15 minutes. So in fact, let's make it 20. So we can start at 3:45 PST, Pakistan Standard Time. So I hope you guys also need a break. So let's reconvene after 20 minutes. So okay, see you all after 20 minutes. Thank you. Hello everyone, welcome back once again. So this is our final talk in the afternoon session. It's about the Mininet, which is an SDN simulator. And the speaker is Mr. Matthew Rahman, who is the PhD scholar here in NUST School of Electrical Engineering and Computer Science, and he is affiliated with the Asi Connect SDON Lab. So I would request Mr. Matthew Rahman to start the session. I hope that you will enjoy, after some theoretical talk, you will enjoy a practical session as well. Okay, so over to you, Mati. Thank you.
Thank you, sir. I'm Hafiz Matthew Rahman, as introduced by Dr. Arsalan. I hope everyone can view the screen. Okay. So this is the brief outline for what we will cover today. We'll start from introduction to Mininet, then installation, that how can we install Mininet, then Mininet commands, and some of the topologies, default topologies, and the custom topologies that we can build from the using Mininet for SDN based networking. And in the end, we will have a demonstration live on the server that we have in our lab.
Okay, please give us a minute to get things technically ready. The screen is shared with all of you, right? And we are audible.
I hope you can listen to me now clearly. Okay, thank you. Okay, so let's start. First of all, let's have a brief overview of the test bed that we have in for networking. Really, when we plan to test our environment or our topologies, to build some topologies. So we have actually three options. Either we can go for the hardware test bed, and for that we need the actual hardware, actual switches, routers, and links, and all the stuff in actually in hardware. And that's of course is very expensive and not very cost effective, and also difficult to handle to change in terms of hardware. So the other option is the simulator. Either we can get a simulator. So simulator actually simulates the software of the hardware and make you unable to build your own topologies or emulate a device in a software environment, so that you can play with the functionality of the hardware in a software environment. That is also has some issues, that it do not accurately or 100% mimic the actual hardware, because when we emulate a hardware or convert a hardware into software, 100% of that cannot be done using a simulator. So only the software part is done. So as far as the emulator is concerned, is a better option, because it can actually replicate the whole hardware and the software as well. So you can mimic the buffers and the queues available in the hardware available through emulator. You can play around with those features that are available solely in the hardware, apart from the software as well. So this is a better option. So let's take a small example that if we want to test or build a very simple topology like 2 hosts and a switch, what are the options? So we can actually fully virtualize the whole system. Like we can have a VM-based server, or we can have 2 hosts, 3 and 1 and 2, and connect them through virtual switch in a virtualized environment. So here, the host machine has all the softwares like Linux kernel and other softwares that may not be required. But this is one of the options that, as I have mentioned, the option 1, in which you can virtualize an environment, implement a practical situation in the software. So the other option is to remove unnecessary software and go for the lightweight virtualization, where you only implement or have only those features which are required for the particular scenario. So for this purpose, Linux offers you the namespace option, the network namespace option. So you can have actually a server, a VM, a server or a VM here, and a Linux kernel. And on top of that, you can instantiate 2 network namespaces instead of 2 actual hosts, like we do in the VMs. So instead of having 2 different VMs, you can have just 2 different instances of the namespace. So namespace 1 will mimic the host 1, and namespace 2 will mimic the host 2. And they are connected via this software switch, open switch module available in the Linux kernel. So through this Linux based software switch, hosts are connected via this link. So we have in fact the virtual Ethernet connected through the switches as well. So as well, you can see in this slide. So we can actually go further beyond that, and we can actually remove the whole Linux kernel, and we can have just a single namespace called the root namespace. And in that namespace, we can have further 2 instances of the namespace, like network namespace 1 and the network namespace 2, and a simple software switch, nothing else. So you have actually all of that we initially saw, that we want to implement that. And now we have very, those softwares which are actually required, those features which are actually required, not the whole VM, not the complete, but the features that are required actually. So we have actually Firefox, a web-based application running here, and an HTTP daemon running on the other host, and a software switch connecting those hosts. Very simple and very lightweight on the hardware to implement. So this is the catch, and this is what the Mininet does. And Mininet gives you the option to build your environment, a Linux in Linux, in your hardware or your topologies, any switches, routers, or the controllers. So you can build any topology that you want in using this mechanism through virtual machine. Through Mininet. So this is how in Linux before Mininet we have been doing. So we have to do all the things only to say this simple topology, like 1 switch and 2 hosts and a controller. So if we want to implement this, we have to write all this code, creating the host namespace, switches, links, and then connecting them through the. So for this purpose, we have to write a lot of code. So Mininet solved this problem and gave us a simpler environment where we do not get involved in writing much of the code. but only the few APIs and few commands that are required to be used for building complex and simple topologies. So getting away with this side some effort, we have a better option like the Mininet, which is an emulator and gives you an opportunity to create realistic virtual SDN based network. So this is a better platform where you can build your test environment or topologies and SDN based network element with that. So host and in this Mininet, like we saw in the previous slides, are using the have a complete standard Linux based environment. Open, and the switches have the open flow capability, as you have been listening throughout today, that the SDN based communication requires open flow for the communication between controller and the switch. So these switches which are available in Mininet are open flow based switches, and you can once experimented, you can very easily replicate and translate and transform your whole scenario into the real world without any further a lot of modification. Just with a few minimal changes, you can implement the whole topology, the whole scenario in the real world very easily. So Mininet is actually a Linux-based tool and is not available for the non-Linux-based environment currently. But that's not an issue because most of the simulator like NS2 and NS3 and OpNet are all Linux-based, and most of them support this Linux-based environment. And most of the work that we required in the research can be done in the Linux-based environment. So that is actually not an issue if we don't have a non-Linux-based tool. So Mininet is solely a Linux-based tool. So there can be controllers which can run on the Windows-based environment or the other environment. So that is not an issue. You can connect any piece of software, any Windows-based system with this Mininet once you have a Mininet topology up and running. So we'll see shortly that how we can do all these things. So first of all, let's discuss how we can install the Mininet. So there are three options. You can either go for the pre-installed version of the VM available on the site. The link is given. You can just download the image and use the VirtualBox to use this VM with the pre-installation of the Mininet, and all the things are set up. The other option is you can simply git clone, and after git cloning, you can just go into the directory and use the Mininet from there as well. The third option is to install from the package. So these three are the options. So obviously, the very easy option and for the beginner would be to use the VM-based installation instead of building all the things yourself initially. So these are few commands that we will be practicing in the demo, and I will demonstrate that how we can use these commands, the variants of these commands, to test different scenarios and to build different topologies, in fact. So mn is the basic command that is used to invoke the Mininet. Simply, once you have installed the Mininet, then you can use simple mn command to invoke the Mininet. And if you want to give further, argument, like you can tell that invoke Mininet with this topology, like tree topology, with depth 3 and the fan out 3, means that every switch will have 3 hosts attached to it, and there will be a depth of 3. In fact, a tree of level 3. This will be a tree of level 3. And you can also set the bandwidth of each link. So every link will be of 10 Mbps. So you can actually play around with the bandwidth and delays of the links as well while creating the topology. And then you can also use the Wireshark within each host. So here, H1 hash means you are inside the host 1. And inside host 1, once you have actually created this topology, you can go inside any host like H1. And inside H1, host 1, you can invoke Wireshark to capture the packets live. And then in the second host, you can run a simple HTTP server application. So in fact, these hosts, as we discussed earlier, has a standard Linux software available in them. So you can actually consider those hosts as a separate VM, but they are actually not as heavy as the VM. They are very lightweight, small instantiation of the namespace instead of the whole Linux kernel. And so pseudo MN topology linear. So you can have tree topology linear and mesh topology and other star topologies. So you can build. These are some custom, built-in topologies that are available in the Mininet. But you can also create your own topologies, the custom topologies, using the Python script. So if you have your own script like custom.py, then you can tell the Mininet that instead of invoking or building these topologies, you can tell the Mininet that build the topology using this script. So the Mininet will create the topology using this script. So here are some few commands that are also useful in Linux in Mininet. So this is the scenario that we saw earlier: a simple switch and a controller and two hosts. So this is the minimal topology or the default Linux, Mininet topology. When we say sudo or this mn without mentioning any topology, the Mininet will create this topology: a controller, a switch, and a two hosts connected to the switch. And if you want to write your own script, then these commands are useful. You can write script, as you can see here. This is add host, simple net.add host command, as evident from the name, very clear that this is used to instantiate a host, or you can add a host in your topology using this command. So add host h1, you are actually adding a host to your topology, and similarly add add host h2, the second host, and the add switch command for adding the switch. So in fact, it is telling that how this topology is created by default or written in the Python script. So this is what we will see in the Python script, that these simple commands will be used for creating different type of topologies or custom topologies, or simpler, or in fact topology of any complexity that you can think of. So net.add controller is used to add the controller. So these few commands here, like adding the host, switch, and controller, are most of the time you will be dealing with these few commands. The rest of the things mostly remains the same. Or you do, for the beginners, you don't actually need to change whole of the Python script, but just to add few lines or to change few lines to test different topologies. And then you will add the links between the host, like h1 and s1, add link between h1 and s1. So host 1 will get connected with switch 1, and add link h2, and then host h2 will get connected with s1, and then start. So once you start the topology, everything will get set up. The topology will be created, controller will be attached, and you will get the console of the Mininet. And in that console, you can actually test anything or run different commands for testing the communication or different parameters that we will see shortly. So here in the next command tells that h2. So this command will be run on the h2, host 2. And the command is that simple HTTP server. So in fact, you are telling host 2, you are actually invoking a simple HTTP server on host 2. So there will be a HTTP server running on host 2. And then you are actually assigning an IP to h1, and through that you can actually curl or connect your client with the server to test the web-based client-server communication environment using this simple topology. And in the end, you have to kill the Python script and then stop the topology. So this is these are few commands that are necessary for the purpose of writing your own custom topologies. Apart from that, you can also tweak with the different parameters of the links and the nodes as well. So you can actually tell Mininet that you want to actually control the CPU, the percentage of the CPU used by a particular host, the bandwidth and all that. So in this command net.add link h2 s1, the bandwidth is set to 10 Mbps. You can actually set it to any value up to like 10 Gbps. So this is what is available. So you can actually make it like light it like 1 Mbps or 10 Mbps, 100 or 10,000 Mbps. And delays are in milliseconds. So you can actually change. So here, 10 Mbps and 50 milliseconds are set for this link between S1 and H2. That you can see that this is that. And for the host 1, the CPU is given only the 20% of the CPU is given to the host 2. So if you have run or implemented some application running on this H1, like we just saw that we can actually run a whole web-based server on the host. So you can actually run any application running on these hosts. So to not burdenize the whole system, you can actually limit the amount of resources used by different hosts. So this is the way that you can limit the percentage of the resources, the CPU, that can be used by a particular host. Okay, so let's go for the demonstration. Okay. So here is our server. We have different type of controllers that you can see here, and the Mininet VM running here. So this is the virtual machine that has Mininet installed. So we will now practice a few things that we have just seen with respect to the Mininet. So the simple topology that we discussed, the minimal topology, the default topology, can be created and instantiated using a simple command like sudo mn. So here you can see that the creating network, adding controller, adding host, H1, H2, and adding switches. So as we didn't mention any topology, it has created the default topology. We call it the minimal topology, with only one controller, one host, and one switch and the two hosts, H1 and H2. And they are all connected. You can test the connectivity between them using by typing few different commands, like you can tell H1 ping H2. So with this simple command, you can actually test whether are they connected or not. So this is different. This is not like the packet tracer or different or the other simulator that we have. This is actually an SDN based. So all the that we have been listening since tomorrow, or we will actually go through this whole workshop, all 4 days, is actually the SDN based. These are the SDN based networks. So when H1 ping H2, what will happen actually? The flow will go to the switch. The first packet will go to the switch, and switch will never know that where H2 lies. Its table is empty. So it will ask the controller to tell where the H2 is. H2. So the controller will install the rule inside this switch, and then the communication will go on. So you will see a kind of a little delay in the first packet, and then the communication will get smoother later on. So, okay. So the first packet faced the delay of like 1 millisecond, and then after that, once the entry has been entered into the switch, the communication gets so it means that two hosts are simply talking to each other. So this is the simple topology. You can actually have many complex or different topologies that you can experiment with. So let's try some other command as well. So you can have actually the node command to check that how many nodes are there. So it is telling you that in your topology, you have a controller C0, two hosts H1, H2, and a switch S1. You can have another command like next to check what are the links. This is actually information that the SDN controller use to build this topology. SDN based controller has a module to discover the topology and build the topology inside it. And the controller usually use this kind of information, that the links and the net and the host available in the network. And then it create a global network topology and share that topology with the application running on top of the SDN controller. So here you can see that there is a link between H1 and S1 here, and there is also a link between H2 and S1. So you can also check the IP address of a particular host, like you can check like H1 if config, like we do in the normal Linux. So it is actually telling you the interface configuration of host 1. So the host 1 has the IP address of H1 10.0.0.0.1, and this is the the Ethernet, the MAC address of this host. So you can check the network configuration of the second host, like here. So this is the other host, H2. The IP address is 10.0. So by default, it gives the IP address of this from the 10.0.0.0/8 network. You can give any IP scheme to your host in the in this mainnet based topology. So all these commands are available. There are many more commands that you can. If you want to check the whole topology, you can simply type the ping all command, and it will test the communication between all the. So H1 will ping H2, and H2 will ping H3, and all. Similarly, every host in this topology will ping the every other host that is available in this topology. So let's implement that web server that we just saw. We will actually run the HTTP server on host 1, and then we will check through H2 or the host H2 and communicate with the communication between the client and server. So H1 will be the HTTP server, and then H2 will be our client. So let's start this web server or HTTP server in host 1. So H1 Python. Actually, this is the Python base. It supports the Python. So HTTP server. So this is the application that we want to run on this. So you can run any application that you want. You can write your own application, and you can run that application in your host as well. So H1 Python M. Sorry, I will type again. Just give me some time to type it. Here. So HTTP server is now running on H1, and from within H2, we will give the command wget or the command to check the communication between client and the HTTP server through the wget command.
be HTTP.
Okay. So here it will be HTTP. It is HTTP. Yes. So it is giving some error. I think done. Okay. So happens sometime with the simulators. And then we have the wget command to check the communication between the client and server. So H2 type again. H1 Python. Again. Okay, now H2 okay, it's giving some error. Okay, so this is actually the way you can implement a client server using the web-based simple commands running the different servers on the host. So we'll move on and actually test some other commands as well. So I will exit from this mininet and we'll see some other variants of this command, the mn command. So you give the test that I want to build the topology and test this, or I want to run this test on the topology. So this command will run, will actually create the topology, the minimal topology, as we didn't mention any topology here, and will test this test that I will just the ping pair or the ping all. I want to test this, or I want to run this, or it can be any script that I want to run as a test on the host. So the topology will be created and this test will be run. And then the topology will be, tear down. So this command is useful and done. So it took like 5.3 seconds to create the topology in the test the communication. But the topology is created and the testing has been done and the topology is tear down. So this is another variant of the command. You can also, there are many tests available, the default test available with the mininet. You can also tell hyper for testing the TCP bandwidth between two clients. So one of the client will become server and the other will become the client, and it will test the bandwidth between two hosts available. So as you can see, the testing was the TCP bandwidth between H1 and H2, and the result shows that there is like 28 gigabit per second available between two clients in this virtual environment. So you can actually, that's why you can actually build the complex scenarios as well, because the tool is very and give you very high end resource for any type of topology. Okay, so let's move on to the other option. If we want to build our own topology, like here in this script that we have, actually we have gone through these slides in the previous slides actually. So this is the simple script for creating your custom topology. So as I told you earlier that most of the lines would not be changed. So there will be few lines that will be of concern. So adding host, like simple this add host command, and then add switch command, and here is actually there can be another command like add controller command, as we saw in the previous slides. So this is where you can create any topology, the custom topology, using this script. And this, then you will save this script, and here you will name your topology. Like I have named this topology like my topo. Like we earlier we saw the tree topology, the linear topology. So this is the name of the topology that I have given to this topology. And there will be the links between. I have actually given the readable name left host. So the topology will be like this. There will be two hosts and two switches. So one switch 1, switch 2, and the host 1 and the host 2. Switches will be connected to the controller actually. So this is the custom topology. And in this topology, I didn't instantiated any controller. So I have to connect a controller with this topology. If I will not mention any topology while using this, while using this topology, then the Mininet will connect the default controller available with the Mininet. So Mininet has a default controller named OVS, Open Virtual Switch controller, available with it. So if we do not mention any controller in our topology or in the custom topology, it will connect that default controller with the topology, and then you will be testing the default controller available with the Mininet. So we'll see that how we can connect to the controllers that we have, the state-of-the-art controller, like the Fox controller, the ONOS controller, and the other. There are a lot of controllers, SDN controllers, like Open Daylight, Floodlight. So there are many different type of controllers available for SDN-based environment, and you can connect your topology with that controller using the same command. We'll see this. The command is same. The command is same. Sudo mn, and there you will mention where the controller lies if it is not mentioned in the script. Like here, it is not mentioned in the script that where is the controller. So it is a simple topology with two switches and two hosts. You can make any topology of any complexity as you want here. So this is the script, and let's see how we can use this script for creating our custom topology. So the command would be, most part of them would be the same. Like we have sudo mn. We are actually instantiating or invoking the Mininet emulator, and we are telling that we want to use custom topology. So custom -- custom, and after that we have to give the path. There's the path of the file which contains the script for the topology. So the path is, we have it in our home directory. So this is the path. Let me show you that. So in our home directory, as you can see, we have a folder named custom topology. In that folder, I have this script topo.py. So my script lies in this file. So I am giving the path of this file, and then I will just simply can enter, and it is actually has done all the things for me. So Mininet has created the network using the controller, the default controller, because I didn't mention any controller. Okay, so the command was incomplete. So there is another thing. I have to mention the name of the topology. Like I told you, my topo, that was the name of the topology which I gave to my topology in here. my topo. This was the name of the topology. Like we have been doing with the tree topology or the linear topology or for single topology, any topology that should be given with this command as well. So this is, and now you actually 2 switches and 2 hosts. So if you type the command nodes, you can see there are 2 switches and 2 hosts. In the minimal topology, they were 1 switch and 2 hosts. So it is actually the topology that is being created using the script. And the controller is the default mininet controller. So I can run all those commands, like I can ping all to test the communication. 0% drop. Host is connected with every other host in the topology. So now let's see how we can connect to the remote controller or the different controller that we want to connect with. So let's first of all run another controller, a different controller, apart from the mininet built-in controller. So we'll go to the POX, as we have POX in here. So you can actually run simply this simple command. Not simple command. Actually, the command is simpler. I have been testing different things, so you can actually have many things with that. So you can have simply the POX file. So this is actually the script containing the POX controller. So you're actually running a Python script containing the. So POX is actually a Python based SDN controller. So you're actually invoking or running this POX controller, but you have to mention at least one thing, that which application you want to run on top of this controller, because by default there are no application available running, and it will be just like a bare metal controller or an empty controller with no module, no application. So you have to mention the applications that you want to run. So as you can see in the previous slide, I have erased that. I have mentioned a lot of different type of applications. You can actually give it like different routing protocols, different spanning tree application, and any other protocol that you have implemented, and you want to test the functionality of that feature on top of SDN. You can mention any of that application in here. So, but the minimal thing that must be given is the layer 2 forwarding switch. That must be a module that must be there, so that the communication can be done between the hosts. So for that purpose, you have to just tell forwarding. Yes. L2 underscore. So it will be a controller with only one application, and that is the layer 2 forwarding switch application running on top of the SDN controller. So the controller is up, and the IP address of this machine is, let's check what is the IP address so that we can give the IP address. So the IP address of this machine is 10.3.12.204. So we'll give this IP address while running our mininet command. So in here, I have to add few lines like -- controller equals remote. So I am telling that I am adding a remote controller instead of the default controller. I hope it is visible down there. So let me just. I think that is better option. Okay. See, okay. So here it is actually not happen. It is equals to. So -- controller is equals to remote, and then comma IP, and here you will mention the IP address of the controller. Right now it is running on the same machine, but it can be running on any machine, like on a different machine. So you can give the IP address. So I will give the IP address of the machine where the controller is running. So this was the IP address of the machine. And then the port. The controller is listening to the port, and the port is 6633 or 6655. So this is the port number to which the controllers usually listen. Okay. Yes. Usually commas are part of the command, so they cannot be removed. The reason is something else. So okay, custom topology. Okay. Controller remote IP address, and then this is all good, but okay. So the port is, as you can see, unable to connect the remote controller. This 553 remote controller 6633. So this was I was giving the same. Double six double three. Okay, important thing is that when I have mentioned that the controller will be remote, it will not use the default mininet switch controller. So it will use the remote controller, and yes, so it has now connected to this box controller because it was running on the same machine. So it is, if it is running on the same machine, it can be accessed using this the loopback address 127.0.0.0.1. So this can be used for the purpose of calling the controller if it is running on the same machine. If it is not running on the same machine, then we have to actually we must give the IP address of the controller and the port that it is listening to. So usually it is the same port 6633, but right now it is not working. But this is the command that how you can connect to your topology with the remote controller. So let me try again, and then we will move on if it's not working. You can actually give the clean command. Yes. Okay, so it's not working. So let's leave it and move on. So this is how you can connect your topology. Unfortunately, it's not working, but this is the command that you can, how you can tell your Mininet that you want to connect to a remote controller. This is the IP address of the controller, and this is the port that the controller is listening to. So different controller listen to different ports. So you, when you will be connecting to the to a particular controller, we must know that what port number it is listening to and what is the IP address. So this is the basic thing that we can be, that can be done. So let's try a few more commands and then we will end this session. So by this custom topology, and just for the testing, we can actually give some commands like we can shut down a link. If we want to shut down a link between H1 and S3, a link between this switch and this host H1 and S3, we simply have tell that link H1 S3 and down. So the link between host 1 and switch 3 is down. So if you will ping H1 ping H2, when you type this command, what happens is this command will be run on this host. So ping will be run on this host H1 and it will ping H2. So network is not reachable, the message from the controller, because the link is down. And then you can just type the command link H1 S3 up and the link will be up. And if you, it is answering now. So that's how you can actually test different scenarios and play around with different parameters in the topologies. So this is okay. Another command, if you want to test that how much time it is taking to build a topology, you can simply type here test none. So I just want to build this topology and test nothing. So it will create the topology and then just tear down. So it will note down the amount of time taken to build this because if you build the complex topologies, it can take time. So if this time is of concern, you can test that time with this command. So it just took only like 0.2 seconds or 283 milliseconds to build this topology and then tear down it. So this is how you can test different topologies and using Mininet. So any question? Unfortunately, we couldn't run that remote controller command, but that would be other fun if that would have been working. But the command is same. You can tell the IP address of the remote controller and the port number it is listening to, and the topology will be connected to the remote controller. So that's how it is working.
Can you please recheck the previous command and remove the spaces? Before I clear and the port.
Okay, let's just move this. Yes, that could be in between port and yes. That could be the reason. Yes, that was the reason actually. So thank you very much. So this is how it is done. So it, thanks to ma'am you mentioned. So the spaces are not required here. So you can just comma and IP address. So now the POX controller is actually controlling this topology. So this is a very fantastic and very easy way of building your own topologies and creating different topologies and connecting to different SDN controllers. So we will have another session. We will see that in the optical domain, if we want to instance devices in the Mininet and different controllers, SDN controllers with optical, support in them. So you can actually, we will have a session with on this as well. and then we will see how they will be working. So this is that's how it was working. So let's check with that command as well. .3.12.204. So it's working now. So the command is working. So the reason was the spaces between this comma and the IP address. So that's how we build custom topologies and some built-in topologies and connect with the remote controller. And as an example, I have created this custom topology and have used the POX controller. So we have in our lab different controllers up and running, so we can connect to them as well. But unfortunately, the time is running out. So I will take the question and.
No, you can continue. I would just want you to check out the chat messages. So you just, if there, you can carry on, or you're done.
Okay. Yes, I'm done for.
You can conclude. You can conclude
Okay.
your remarks, like if you want, and then have a look at the chat messages for the question. I mean to say, I don't want to rush you off. I just wanted to see the chat message. You can conclude by giving your remarks for the concluding.
Okay.
Take your time.
If there's any message in the chat.
No, not the chat of MST. The chat.
Okay.
There were messages. Okay, yeah, let's go with
This
yeah. So will you be covering flow tables? So okay. They were. Dr. Fahim is asking about open flow tables.
Yes.
You can, yeah.
Yes, we can check the flow tables using different commands that are available on the Mininet website. That if you want to check or you can actually check the POX controller site for testing. Actually, you can run any command in here for testing the flow tables entries in the switches. So yes, I'm actually not covering this in this lecture, but I can guide you where you can find the resource. So you can actually go to the Minutes homepage, and then there you can see the command for testing the flow table entries or different flow tables that are being built. So in fact, you can actually invoke Wireshark in the along with this Mininet. So you can capture different packets and then check what type of messages are being exchanged between the hosts. So that can be done with this. Any other question? So there are different type of application, as I mentioned earlier. So there can be layer 3 switch and any other routing application, but it is as per the demand of the topology. So if I would have used other layer 3 devices in my topology, I must have to use the layer 3 forwarding switch or some related application running on the SDON controller. And you can actually go to the ONOS and Python repository. There you can see that what type of applications are available with different controllers. Not every controller has all the applications. Some of them have a different set of applications. And then you can actually get the code and modify the code for the particular environment. So as we have the ONOS for the optical network, and Anik will be presenting inshallah on that the ONOS controller in the optical environment.
I have a chat message. You can just
yes. Yes, I will share the handout materials, all that we have covered and the set of commands that I have used in this particular session today. Is any other question? Yes. Okay, that's a good question. So you can connect more than one controller. Actually, this is actually what is happening in the SDN domain right now. So the distributed controllers are recommended. Instead of having a centralized SDN controller, we have distributed controller, and we can create different domain of switches and assign a different domain to a different controller. So yes, we can actually add different controllers in our topology or using Mininet. Yes, we have to actually mention which controller. If you go to the slide. No, it is not. The controller is linked to switches not by default. We have to tell the switches, and we have to establish the link between them. So that's how you can actually. Yes. So here you can add link between different hosts and the control switches. Yes, so switches are attached to the in the switches inside the controller. You will actually have an application, the partitioning application, running in this in the controller. So if you want to have a distributed ONOS controller and 2 instances of the ONOS, so you must have to install a partitioning application so that you can assign one category or one set of switches to the controller 1 and the other set to the controller 2. So this is how this is done actually inside the controller. Yes.
You mean to say there is one controller, we somehow there's a partition application that creates partition inside that controller, and then we assign those partitions to different switches.
Okay, so in distributed environment, we have more than one controller, and one of the controller acts as a master and the other acts as a slave. So there is the global view of the topology, the global network view, the whole topology, and then you application, it assigns a set of switches to the slave or to the other controllers available in the same topology or to the in the environment. That's how it is done. Welcome.
So, all right. Any other question from the virtual participants, the online participants? Dr. Fahim, we will share. I don't know if Mati has to first make the manual. It may take a couple of days, but eventually we'll share.
Yeah, maybe by tomorrow I will share.
Yeah, by tomorrow. Sure. Because after you have a talk tomorrow morning.
Yes.
Another chat message. Okay. Yeah, you're most welcome. Okay, so I guess there is no further question by the okay. Thank you very much. Yes, indeed. Thank you, Mati. It was a wonderful
Thanks
session.
for the compliment.
Because the people who actually wants to have a hands-on flavor, yes, the practical, it was in this session. So, and we'll continue the hands-on in tomorrow's session as well. Yeah.
So let me just tell what will happen in tomorrow, inshallah.
Yeah.
So we will be covering different SDN controller, like we just saw the flavor of the box. So I will be using different. We will go inside different SDN controller at the architectural level. So we will cover some theoretical part of the SDN controller, inside particular to the SDN controller, very specific.
Thank you to all of you. Thank you, Dr. Chaturanga. Thank you, Mr. Nirajan, and to all the participants attending who are online, and to all the participants who are Mr. Shibli, Mr. Pong, everyone. Thanks a lot, and to all the participants who are physically present here. So yes, it was quite a long day.
Dr.
Yeah.
Shan,
Mr. Fahim and Mr. Butha. So I think, yeah, most welcome. Thanks a lot. Thank you for the kind words. There's still a lot of coordination and management to be done. There were few lapses today. We'll try to cover them up tomorrow and the rest of the days. So thanks again to everyone for joining in us today.
Dr. Shan,
it was quite an eventful day. We had morning session with introduction, opening remarks, and presentation about our project, and in the afternoon session with the optical communication and this hands-on session. Yes, thanks to all the NREN. Yes, Mr. Alam, thanks to you as well from BDREN. And so I hope tomorrow our starting time is 9:30 Pakistan Standard Time. Okay. So I hope to see all of you, the physical participants, and also thanks a lot. Okay. Yes, sure, Dr. Imran. I'll if everyone can just, I know everyone is tired, just bear with me for just 60 seconds, so I can, as Dr. Imran mentioned, I can just give a brief of why I cannot control this. Where's the where is the no, it's this is the remote. No. Yes. Oh, it's this one. Okay. Yeah, this document. Okay. So okay, we'll just take 30 seconds. So tomorrow's Mr. Mati will continue, and his focus on tomorrow's hands-on session will be on SDN controller, and then Mr. Anik will take it from Mati and move ahead to talk specifically about ONOS controller, which is very famous in both industry and academia, in particular for the SDON use case, software-defined optical networking use case, the one that we are talking about. But obviously, we have to build the basis and then moving towards ONOS. And then we have a keynote by Professor Luca Poti on high-capacity optical communication. There has been a slight change of plan because of the availability of Dr. Jan Kundat from CESNET. He will be talking from 3 to 4 Pakistan Standard Time, and so Dr. Imran will be talking before. So I'll make this swap and share it on the mailing list once again. So this is our tomorrow's plan. Pretty exciting day to follow. Some keynote speeches, Professor Luca and Dr. Jan Kundat and Dr. Imran. So, and the hands-on in the morning. So, okay. So once again, thanks a lot everyone for joining in, and I'll see all of you tomorrow, hopefully. Thank you so much for the participation in day one of it. Thank you. Bye-bye.